On D? So find the instantaneous velocity when t is 3 seconds. So this is the one we were talking about. At t equals 3, what would you estimate the slope of the tangent line to be?
So, I mean, basically I see the line from 2 to 4.
But from 2 to 4, this line's not linear from 2 to 4, right? Because if you pull up the Java application here, it shows you that if you were going to approximate this point P, you can't take this. Let's make it a little bit more like this problem here. So show actual tangent line. If you just said, okay, from this point to this point, you would get close, but it's not actual. So it's kind of ridiculous in this problem. They expect you, 7.2. I was not expecting anyone to pull that up. -5 minus anything from -1 to -10, I give you full credit on that. Same on an exam. What you need to know is how to approximate it. Is it a positive slope? Is it a negative slope? And the values in which it's 0. Yeah. Because there's no algebra here. If there was an algebra function that related it, you could find the derivative and plug in that point, and then you would get the exact value of the slope.
We did a really good practice over it, and I just
Yeah.
that one little equation. I'm like, how do I do this?
Yeah, and it's just an approximation. And I try to show, if you remember from a couple days ago, I gave you pictures of the difference in the slope of the tangent line and the slope of the secant line. Yeah. Okay, so does anyone have any other questions on the written homework?
I do.
Okay.
Yeah.
Go ahead.
11B, I'm not sure where to go with that.
On
2.1.
2.1, 11B. 11B. Okay, so if I can zoom in. We have 11B. Find the instantaneous rate of change at y with respect to x at the specific value x naught. X naught being 0. So we're looking for the instantaneous rate of change, so that's the derivative example. And instead of plugging in x, we're plugging in x equals 0. So we have f of 0 plus h minus f of 0 over h, and the limit as h goes to 0. And then on C, you do the exact same thing, but you take an arbitrary value. So you let that be x naught, and you leave x naught into your expression. So you have f of x naught plus h minus f of x naught over h. Your function is going to be a function of x naught. Does that make sense? B and C are very similar. Here you're plugging in 0 for x naught, and here you're plugging x naught in for x naught. It's a placeholder for any arbitrary value. Help? And then D, you're comparing the slope of the tangent line at the point to the slope of the secant line of this given graph, 2 times x squared. There's one right here.
Oh, there is? Oh, yes.
So do you want to look at that, or do you does that kind of click? What? You graph the function. The slope of the secant line, you're just going to connect those 2 points on the function, right? The slope of the tangent line, in this case, at this value, it is 0, right? Because if I plug it in B, I get 0. So it's the x-axis. But it won't always be that way.
Why do we need to graph?
It's just trying to get you to tie together that these functions are related. And eventually, I will give you a graph of a function and have you graph the derivative on top of it. So you kind of need to know how it works. And that's what we did in class yesterday. We calculated. So yesterday we did this example where we found the derivative of this algebraically by using the definition. Do you guys remember doing that? You slept since then, so. And then I graph it on top of here. Eventually, I'm just going to give you that the black function is the function and graph the derivative on top of it. And you should be able to say, okay, well, I have a slope here of 0 and a slope here of 0. So my derivative has to go through the x-axis at these points. because the value of my derivative is 0 here. And then here I have my slope is positive, meaning the value of my derivative needs to be above the x-axis in this interval, because my slope is always positive in this interval. In this interval, my slope is always negative. So my first derivative needs to be below the x-axis in that interval. And then in this interval, my slope is always positive, so the value of the function is above the x-axis. So eventually the reason why they're having you do it algebraically and then graphing it is hopefully you can build some of those relationships when you see it. So when they give you the function they ask to match the graphs of the derivatives, you'll be able to do that.
And we knew it was like a squared function because we solved it
Well, we did this algebraically.
down here.
It wasn't down there. It was in on the previous page, right? We did this example, page 2 of the notes yesterday. We went through and algebraically got this representation for the derivative. So then I had the function and the derivative. I could graph that, and then I can compare them. Eventually, I think this is your homework on 2.2, and I know 2.2 is not due, but let's pull that up. Here. This example, I think 23 I have you turn in. And it says, match the graph of the functions with the graph of their derivatives. So, if I look at this, so this is A. What's the value of the derivative on this interval? Positive. And what's the value of the derivative here? 0. So I need some kind of function that has a positive slope and then 0.
D, capital D.
Capital D, right? So A goes with capital D because I have a positive slope like 1. Yeah, let me pull this up on Wiley. So this is 2.2. Standard view, full screen view. It's number 23. There we go. So, see if I can. 23. I'm zooming in, I need to zoom out. Okay, so printer version is going to give me a better chance to zoom in. Okay, so can you see that a little better than the document cam? So A, I have a positive 1 slope, and then it goes to 0. Positive slope, then goes to 0. So let's do B. What could you match the graph of the derivative of the function B? I have a negative slope, then a positive slope, then a negative slope, then a positive slope, a negative slope, then a positive slope. It's going to be F, right? Negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. Let's look at C. What would the derivative of C look like?
It's almost 0.
It's almost at 0, then it's positive, 0, negative, and then 0. Okay, see that? So here would be 0, 0, positive, 0, negative, 0, close to 0. And that's the only one that fits there.
When is it negative on C?
On C, the slope is negative when x is positive. Right here, the slope is negative. Oh, does that make sense now? So you can see on B, the value of the derivative is above the x-axis from minus infinity to 0, and below the x-axis from 0 to infinity. Because the slope is negative when x is positive, and positive when x is negative. So let's look at D. I start off having relatively 0 slope, and then my slope goes negative infinity, and then over here it goes from positive infinity to pretty much 0.
So C.
Yeah, so the slope over here would be positive a large number. So it would look like this, right? Because my slope would be close to 0, and then it's getting larger and larger negative, and then but it's going to 0. Question? Okay, is this, you guys kind of see how these two graphs are related? Given the graph of the function, being able to graph the derivative on top of it, but you could also go the other way. Given a derivative, match it with the original function. So both ways could be asked on that. So we'll finish a little bit, we'll do just a little bit more on 2.2. I have some technical notation I want to kind of go over. But homework questions, what was 1.5? 1.6?
It's 13 or 17. It's not on my
1.6, I was on the book. 13 or 17? We did 13. Here? So this, you have to know a little bit about inverse functions. Number 13. So we're looking at the what's it want? When this function is not continuous. So let's write this one up. Okay, so today is, everyone's aware the homework's due tomorrow by 5 o'clock, right? I'm not going to write that question.
Is it Q2.1 or Q2.2?
2.1. The reason why it's from 2.1 is because your exam next Thursday will cover through 2.1. So I'll just go ahead and write this in here. Oops. 13. Okay, so homework from 1.1 to 2.1 due the 8th by 5 o'clock. If you have your homework done, you can turn it in today. You're going to turn it in 307E of Mannheim if you don't turn it in today. And you can turn it in any time by 5 o'clock on Friday. So there will be, if I'm not there, there's an envelope on my door. You can slide it in. Okay, so we have a homework question. This is, what section was that? 1.6, number 13. Pull that up real quick. So we're given the function. Is it not assigned? Is it a different problem or? Number 12, the exponential. Okay, so number 12, we have f of x equals e to the sine of x over x. And we want to know when this is continuous. It's continuous when the function exists, or when you can plug in what values of x is this continuous for. So do I have any problems in what I plug in e to a power? Huh? Kind of starting on the outside. Can I plug in any number to sine of x over x? I can't. What can I not plug in? 0. So here x cannot equal 0. Can I plug in any other number?
And it cannot equal negative, right?
No, e is fine. E can be, well, e to the negative 5 is e to the negative 5. You can plug that in your calculator. It's natural log. You can't plug in 0 or negative. Sometimes it helps to draw the graph. E to the x looks like this. ln of x looks like this. Right? So you can see clearly I cannot plug a negative number into ln of x, and I can plug any number to e to the x, but it will never be 0 or negative. So here, the only concern we have is when x is 0. Everything else is perfectly fine, and it's going to be continuous. Question? 1.6, 50? 1.6, 50. So we have asking if this function is continuous. So we have this piecewise defined function, and it's defined as sine of x over x, the absolute value of x, if x does not equal 0 and 1 if x equals 0, right? Is this function continuous? What do we need for continuity? Okay, so that's part C, right? But even above part C, part B says the limit has to exist at all points.
Yeah, it has to always be defined.
And the function has to be defined. So if I plug in 0, I get 1, and if I plug anything else, I have a defined function. So it's defined at every point. So part A passes. Part B is actually where we need to check. The limit on the right needs to equal the limit on the left to equal the value of the function at the point. So we know for continuity, we need the limit as x approaches 0 on the left of the function to equal the limit as x approaches 0 on the right of the function to equal the value of the function at 0. If this fails, it's not continuous at x equals 0. Question?
You said, the first thing you said is 1
0
into the x's?
until the function f of x. This function is defined as sine of x over absolute value of x if x is anything other than 0. We don't have a problem plugging anything other than 0 in, right? If I plug 0 into the function, then the function is then explained as 1. So now if I look at the limit on the left, so I have the limit as x approaches 0 from the left of sine of x over absolute value of x. Compare that to the limit as x approaches 0 on the right, sine of x over absolute value of x. That should equal 1. If it equal 1, we deal with absolute values in a limit. We need to replace them. Remember talking about if x is negative, I replace the absolute value of x with minus x, right? If x is positive, I replace the absolute value of x with x. Does that make sense? And just to kind of go over this a little bit more, whatever I have in the box is x, right? So if I have the absolute value, and I'm saying these are equal to each other. The absolute value of 5 is 5, right? But x is minus 5. So I have to have this minus 5 over here. And what's one way to change minus 5 to positive 5? Multiply it by negative 1, right? So it turns out the absolute value of x equals minus x if x is negative, right? And then, of course, the absolute value of x equals x if x is positive. And this just kind of explains why you can do that. Because whatever I put in the box is x, so I need my x to be represented over here. When I take the absolute value, I just get a positive 5. So I need to make sure I multiply this side by negative 1 so that it's a true equality. It equals. So evaluating this limit, is x positive or negative? Negative, because it's always on the left side of 0. I mean, it's always negative. So I can replace this as the limit as x goes to 0 from the left of sine of x over minus x, right? Here x is always positive, right? I get the limit as x goes to 0 of sine of x over x. What is the limit as x goes to 0 of sine of x over x? 1. And then here, what's the limit as x goes to 0 of sine of x over x? We said was 1, right? But this actually turns to be negative 1.
So it's not.
Very good. So we've concluded this function is not continuous at x equals 0. It's not continuous because the limit doesn't exist at 0. So we can't even begin to say the limit on the right equals 1, but the limit on the left equals minus 1. So it's not a continuous function. Any other questions on the written homework?
Is that 1.650?
Yes. Was that?
1.5 number 13.
Absolute value sign.
Yeah, so here I can just kind of 1.6, number 50. Absolute value. Okay, there's a hand back up, so what's your question?
Another proof. This is on Wiley.
Mm-hmm.
I got them all right, where you can say, okay, that's 17 over 4.
Mhm.
I just feel like I'm still stumbling
On how to show that?
up the proof. Yeah.
Well, we did one of those a couple days ago, and I'm just going to pull that up to kind of save some time in class and talk about that. When we talked about the 1.6, we did an example where we had, the limit as x goes to 0 is tangent of 17x over sine of 2x. So we know that's going to be 17 over 2 because we've done enough of these and it always ends up to be that. But to show that, you can only use the fact that sine of something x over that something x goes to 1. So you want to rewrite tangent as sine over cosine. And then manipulating this, so I pull out the cosine because 1 over cosine, I'll deal with that later. So yes, you can separate. Anytime you have multiplication, you can separate that out. So there's nothing being added or subtracted here, so I can write these totally separately. So if I take sine of 17x over 17x, I know that goes to 1. Well, I manipulated this expression, and I can only multiply by 1, but I wrote 1 to be 17x over 17x. So then I pulled the 17x in the denominator to group that with sine of 17x over 17x, because that goes to 1. But I still have this 17x to deal with later on. Does that make sense? So, really I wrote 17x over 17x, but I wrote it in a way that this is going to be grouped and go to 1. Same thing here with the sine of 2x on bottom. I take 2x over 2x, but I group this because it's going to go to 1. So then I'm left with this expression. I don't have to necessarily write it this way, but simplifying it, I have a 17 on top. I'm left with this cosine of 17x on bottom. Perfectly fine to leave that because whenever I plug in 0, it goes to 1. It doesn't give me a problem. Here, if I plug in 0, I get 0 over 0, which gives me problems. So I want to get rid of the sign in the denominator, and I can do that. And then at this point, when I plug in my limit, I have 17 over 2. Really, I have 17 over 1 times 2. But does that make sense on how to show that?
Should I just memorize how to do that, pretty much?
The process, yeah. You want to memorize kind of the process and then be able to apply it on any number. No, you need to multiply top and bottom of this sign expression by whatever is in the sign. Same thing with this one. Simplify it and go from there. Question?
1.5, number 13.
1.5, number 13. So this has to do, show if a function is continuous or not. So let's look at, pull the notes. Okay. 1.5, number 13. You're given the function f of x equals x plus 2 over x squared plus 4. Where do the problems lie? Anytime you're asked for continuity or if a function is continuous or not, you want to verify where the problems lie and then make your conclusion on that. So, do I have any problems here?
Yeah.
I do?
No, sorry.
Theoretically, we'd say, okay, maybe the denominator could be 0. So, if x squared plus 4 equals 0, I have a problem. Right? But that would mean x squared would have to be negative 4, which there's no real numbers that makes that, right? So this is continuous from minus infinity to infinity. Basically, there's no problems. So we're happy. Question? 1.3, number 27. So this is one where you have to divide top and bottom by the absolute value of x, because we have this radical. So this is, so we're given, you said 27, right? Yeah. Okay. So we have the limit as y goes to minus infinity of 2 minus y divided by the square root of 7 plus 6y squared. So anytime you have a square root, the method of taking the highest power of y in the numerator and the highest power of y in the denominator might mislead you, especially when y is going to minus infinity. Right? Because this. So you want to divide top and bottom by the absolute value of y, and it turns out the absolute value of y can be replaced with minus y when y is negative, right? Again, with the concept there. The absolute value of y can equals the square root of y squared. So this would be the limit as y goes to minus infinity of 2 minus y over the absolute value of y divided by the square root of 7 plus 6y squared divided by the absolute value of y. So everyone at this point can agree we divided the top and bottom by the same thing. I only multiplied this expression by 1 so it doesn't change the limit. So I can do that. On top, I'm going to replace this absolute value of y with minus y because I can't deal with absolute values and limits. I need to simplify those. Since y is going to minus infinity, I end up with the limit as y goes to minus infinity of minus 2 over y plus 1. And then I rewrite the y in the denominator as the square root of y squared, so I have 7 over y squared plus 6. Does everyone follow me to that point? So we're getting close. The limit as y goes to minus infinity, I have, well, I don't even need the limit anymore because I'm going to plug it in. I have 0 plus 1 over the square root of 0 plus 6, which gives me 1 over the square root of 6. You could write that, and I don't know if your book rationalizes it as the square root of 6 over 6. Okay, sometimes it does. So. Okay, does anyone have any questions on problems like this? Sometimes students will look at this and say it's going to be 1 over the square root, negative 1 over the square root of 6, but you have to be really careful because y is going to minus infinity. If y was going to positive infinity, it would be minus 1 over square root of 6, and you could show that by doing this work.
Right, so it is positive?
This answer is positive.
Because that's right at the negative 2 over y.
Mm-hmm.
Does that just go to 0 too?
This expression goes to 0 because y is going to infinity. It doesn't matter, yeah. Anything over something going to infinity goes to 0. Plus or minus is still going to go to 0. Plus or minus 0 we don't worry about. Does that...
Do you also factor out the minus?
We're not factoring it. I mean, here I'm replacing this with minus y. So I have 2 over minus y, which is minus 2 over y. Minus y over minus y, which would be plus 1.
Wouldn't you have a problem if we divided by y instead of minus y?
If you divided by y, it would be fine, except for the fact you couldn't rewrite y as the square root of y squared. The reason why you divide by the absolute value of y because it's convenient, because the absolute value of y equals the square root of y squared. But the square root of y squared doesn't equal y. It equals the absolute value of y. Because if I think the square root of negative 5 squared, that's 5. So you have to be careful with that.
This method, I mean, this is the second time we've seen this method.
Yeah.
This is only applicable when you have a radical denominator.
No, it's applicable in any time you have a polynomial over a polynomial. But when you have a polynomial over a polynomial, you just take the highest power of your variable in your numerator over the highest power variable, and you're simply doing this. It's just simplifying it.
Sure.
Because if you think about the highest power of x in your denominator, all the other terms are going to go to 0 anyways.
Right.
So you can just forget them and deal with that. But in this case, you can't because you have this radical and you have something going to maybe negative infinity. So you have to be careful with your negative there.
Okay. Well, I think what is asking is would we have to do the same process if we had the radical on top?
Yes.
Okay.
Yeah. You do the same process when it's in the numerator. But you could do the same process with a polynomial over a polynomial. The method is foolproof in any instance.
Okay.
But there's quicker methods in different instances.
Okay.
Any questions? Okay, what was the next homework question? Okay, this will probably be the last one I have time for, so I can write up some stuff on notation and give you time. 1.3, number 39. Okay, so I think I talked about this one in class, didn't I? The limit as x goes to infinity of x plus 1 to the x power over x to the x. I talked about this one in class with you guys. I have 2 Calc 1 classes, so sometimes I'm like, I did this one. Yeah, what's it going to? It's going to e. You can show that the limit as x goes to infinity of 1 plus 1 over x to the x power. That's the same thing. If I have something like a to the b power, or let's say x power, and b to the x power, I can write that as a over b to the x power. This is e by definition. Okay, so 2.2, day 2. So last time we covered some good examples on 2.2. We did the example where we had, did I grab that? Am I missing a page? Okay, we did the example where we had x cubed minus x. And then we also did the example where we had 2 over x squared, right? I don't know where that page went. We did 1 over x squared, sorry. We did 2 over x a couple days before that. Go ahead and pass around the sign-in sheet. Okay, so maybe... Okay, so some things I want to comment on in this section. So the application, did I do computing? Did we talk about computing instantaneous velocities? And I wrote that the first position, the derivative of position is velocity. Do you guys have your notes from last time?
I don't write stuff down.
You don't write stuff down? What about, where were you? Sorry guys, I don't know where that other page went. I don't want to.
Mine are super sloppy,
But
but
that's okay, I can see.
there's instantaneous rate of change.
Okay.
So examples we did.
Okay, good. That's where I thought. Okay. So computing instantaneous velocities. Some of the applications in this section, they won't say find the derivative. They'll say find the velocity. So the first derivative of position is velocity. This is very useful in physics. So if I have a position function, and a lot of times your book writes, f of t. Sometimes they'll write s of t. These will be position functions. So you might have f prime of t. That you might write that as v of t. So it would be your velocity function. So you might see something like the derivative of position equals velocity. Position, velocity, and acceleration are all concepts that are studied in physics a lot of times. If I drop something, I want to know what position is it at any given point in time. I might want to know how fast it's going at any given point in time, and I might want to know the acceleration at any given point in time. And it turns out they're all related. Derivative of position is velocity. The derivative of velocity is acceleration. So the applications of this section have to do how things fall to Earth. And it turns out, if I write out, well, I could have some fun here. Does anyone know position function for objects falling on Earth?
I have one here in a second.
Well, that's the acceleration, right? It's a constant acceleration, which is important. So the acceleration is a constant, and they name that g. The velocity function, if I want to know how fast it's going, it's just going to be g times t, right? So this would be g times t, and it turns out maybe plus initial velocity, depending on if I give it some initial velocity. Then it turns out the position is 1/2 g times t plus the initial velocity times t plus the initial position. Do you guys know these equations from physics? You ever seen this equation before? 1/2 the gravity times the time it's falling. If I drop a rock and I'm 500 meters above the Earth's surface, and I want to know where it is at after 2 minutes, I would plug t into this function. And g would be 9.8 meters per second, or 32 feet per second squared, depending on what units you're using. If I have an initial velocity and initial position, all these are related. If I differentiate this, I get this. If I differentiate this, I get a constant g. Eventually, in Chapter 5, we'll learn integration, and we'll learn how to go backwards. So it's called rectilinear motion. It's a huge part of physics, and so if you've been in physics, sometimes they teach you how to find derivatives by the power rule or the product rule, things like that, so you can deal with these physics types problems. So I want to give you time for your quiz, and so I will finish the last